Hello student, it's nice having you on today's lesson. In today's lesson, we shall be taking a look at ideal gases. In this lesson, we will be looking at what ideal gases is all about. What ideal gases really entails as far as Cambridge syllabus, A-level syllabus is concerned. Well, there are some basic things that you have to understand for you to be able to comprehend this concept of ideal gases. Those basic things are the first things we are going to look at before considering the topic properly. Well, from the beginning of the general physics that is under physical quantities, you must have been taught fundamental quantities as well as derived quantities. Well, my major concern now is the angle of the fundamental quantity. I want to see how some of the things you learned then can be related to what we want to learn now. One of the fundamental quantities is amount of substance, which is measured in mole. That very fundamental quantity is very important as far as ideal gases are concerned, because we will be making an allusion to it during the course of today's lesson. So we will be looking at what a mole is all about, as well as some other basic things that we'll need to know for you to have a better understanding of this concept, ideal gases. So the question now is, what is a mole? What is a mole? Well, a mole is the amount of substance, take note of that word, amount of substance containing same number of particles in a 0.012 kg or 12 gram of carbon-12. There are two salient points there that you need to take note of, and that is the word amount of substance. Just as I said the other time, that one of the major fundamental quantity that can be related to ideal gas is amount of substance, which is measured in mole. So a mole, in all the sense, that is one mole, is simply the amount of substance or quantity of substance that is contained or that is containing same number of particles. Same number of particles. That is another key word that must be taken note of. Number of particles in 0.012 kilogram, or if you convert it to gram, 12 grams of carbon-12. So in other words, this is simply telling us that in one mole I can find a certain amount of particle in just one mole of a given substance, and that given substance could be carbon-12. And mind you, that same one mole is as well equivalent to the relative atomic number of that same carbon-12. That is why we said in 12 gram of carbon-12, because 12 gram is representing the relative atomic mass of carbon. Please take note of that one mole is also equivalent to the relative atomic mass, not atomic number, please, because the relative atomic number of carbon-12 is 6. So it is only equivalent to the relative atomic mass of carbon-12, which is very, very important. So we'll be able to relate 3 important things here. One, we'll be able to relate the fact that 1 mole is equivalent to number of particles that is contained in carbon-12, and is as well equivalent to the relative atomic mass of carbon-12. And that's what I have right here. That's what I have right here. So you need to take note of this fact. For example, I can as well say that 1 mole of nitrogen is equivalent to 14 grams of nitrogen, because the relative atomic mass of nitrogen is 14 grams. And since I said 1 mole is simply the amount of a substance, and the substance could either be carbon, any element whatsoever. So 1 mole of such a substance, which could be nitrogen, is equivalent to the relative atomic number of that element, which is 14 grams of nitrogen. It could be any other element apart from nitrogen. So this is a simple example of what I'm simply explaining. Now there is another thing we need to know before we go deep down to dissect what ideal gases is all about, or are all about. Another thing we need to know is the concept of Avogadro's constant. So the question is, what do you know about Avogadro's constant? Well, you must have been introduced to this in chemistry. It's as same to physics. So what is an Avogadro's constant? Well, an Avogadro's constant, which is usually being represented by capital letter N subscript A, is the number of atoms of carbon-12 in a 0.012 kg or 12 grams of that same carbon-12. There are 2 salient points right there. One, Avogadro's constant, constant is simply the number of atoms. Number of atoms of carbon-12. This carbon-12 could be any other substance, not necessarily carbon-12. It could also be any other element. Now, in 0.012 kg or 12 grams, this value could also be the value of any other element, which is the relative atomic mass of such element. So that's why I say it's not necessarily carbon-12 this time around. If I'm considering nitrogen now, then I'll be saying number of atom of nitrogen, 14. And I will say in 14 grams of nitrogen 14. So we're still saying the same thing right here. So those 2 key points, the number of atom as well as the relative atomic mass, is one of the key points that must reflect when you are defining the word, Avogadro's constant. This is what is expected of you. So I can simply conclude that Avogadro's constant is equal to the number of atoms, or you can as well say 1 mole of atom. You can also say 1 mole of atom. Why? Because 1 mole of atom, from what I explained the other time under mole, is also equivalent to 12 grams, which is the relative atomic mass. So if the Avogadro constant is equal to the number of atoms, so it's the same equal to 1 mole of the same element. Now, knowing full well that this is a constant, that means it comes with a fixed value. Avogadro's constant comes with a fixed value, and that value is 6.02 times 10 raised to the power 23 per mole. I take it again, 6.02 times 10 raised to the power 23 per mole. Now, this can be summarized as it is right here. So here I have my Avogadro's constant, Na subscript A, equals the number of mole or 1 mole of atoms. Since 1 mole of atom is as well the same as the relative atomic mass of the atom of that element. Now it's also equivalent or equal to 6.02 times 10 raised to the power 23, which I've simply said. Now you need to take note of some certain things as far as atoms are concerned. Now, one of the key things you need to know is the fact that the more the number of atoms of an element, the more the number of molecules. What do I mean? The more I have atoms, the more I have molecules. Actually, molecules are combination of 2 or more atoms. So if I have more atoms, obviously, since molecule is a combination of 2 or more atoms, definitely the number of molecules will increase. Now, as the number of molecule increases, the more is going to be the number of mole of the atoms of the substance. So 3 things are concurrent. The number of atom increasing will increase the number of molecules formed by the element, and the more is going to be the number of mole of the atoms of that substance. So that is how the progression goes. So the quantity increases, the quantity of mole increases with increasing atoms or molecules. Now, another thing you need to take note of is that since we are dealing with more than 1 atoms, then we can say that Avogadro's constant is equal to number of atoms, n, I mean capital letter N, divided by number of mole, small letter n. We use small letter n to represent the number of moles, and we use capital letter N to represent number of molecules. So I've been able to give you 2 different relationships between Avogadro's number, constant, and number of molecules, and to number of atoms. Then I gave you another one the other time, that Avogadro's constant is as well equal to number of atoms or 1 mole of atoms. So we have 2 different relationships, and you need to master those relationships. It's very, very important. Now, in this case of the relationship we have right here, we can conclude that in 1 mole of molecules of a substance, 1 mole of the molecule of a substance, we are going to have relative molecular mass, which is Rmm of the substance in gram. That is, 1 mole of the molecule of a substance will give me relative molecular mass of that same substance in grams. This is completely different from the one I gave you initially. I said 1 mole of an atom is equivalent to relative atomic mass. That one is for element, just an atom of an element in gram. But this case, I'm having more than one atom, because more than one atom is making a molecule. So 1 mole of the molecule will make a relative molecular mass of the same substance in gram. A good example is this. If we have 1 mole of nitrogen molecule is capital N subscript 2. Why nitrogen atom is just N. So that means here I am having twice of the nitrogen atoms. So if I have 1 mole of nitrogen molecule, it will give me the relative molecular mass of the nitrogen molecule, which is 2 times 14. Knowing full well that 14 gram is just for 1 mole of nitrogen. But since I'm now having a molecule of nitrogen which is twice of the mole, so it will be twice of 14 gram, which will give me 28 gram. And that's what I was trying to explain right here. So if it is atom, it will be equivalent to 14 gram, which I've earlier explained. But if it's molecule, 1 mole of the molecule will give me 28 gram. Now, there are certain things when we come to the aspect of mass of a given substance. For a given mass M of a substance of molar or relative molecular mass capital M, the number of mole N, small letter n now, becomes this. Small letter n equals small letter m over capital letter M. And each of these entities represent what they've been representing, where n is a number of number of mole rather, and small letter m is the mass of the substance, which I have right there, and capital letter M is the relative molecular mass of that same substance. This is a relationship between the mass of a given substance and its relative molecular mass, relating it to the number of mole. So when we are defining number of mole in terms of masses, then this is a correct expression for that, which is, this alone is going to give us something unique in terms of gram per mole, because mass small m is measured in gram, capital letter M, which is the relative molecular mass, is measured in gram per mole. So at the end of the day, gram will cancel gram and it will give me mole. So at the end of the day, I'll be arriving at the unit of the number of mole, which is the amount of substance right there. From here, we can now consider the concept ideal gas, having undergone the basic things we need to know for us to able to understand some things as far as Cambridge syllabus is concerned. What is an ideal gas? An ideal gas is the one that obeys gas laws or equation of states. When you have a gas obeying gas law or equation of state, that is just one out of the factor that qualifies such a gas to be an ideal gas. But that is not all. Now, when it obeys gas law or equation of state, when the mass or an amount of gas, which is a mole, is constant, then that gas becomes an ideal gas. So I'll be able to give you the second factor that qualify a gas to be an ideal gas. So the key point you need to take note right there is this word gas law or equation of state. Once the ideal gas obeys that and its mass and amount of that gas is constant, does not change, then it is an ideal gas. So those are the two key points that you need to take note of when defining the word ideal gas right there. Now, equation of state is written as this: PV equals nRT, where P stands for pressure, V stands for volume, N stands for amount of substance, which is a mole or number of mole, then R there stands for the molar constant, and T stands for the temperature, or you can call it the thermodynamic temperature. And each of these entities right here that I have are also constant, because at all values of P, V and T, at all values of P, V and T, all values. So in other words, what I'm saying is the fact that mass is constant, this is constant, the amount of gas, okay, at all values of P, V and T. That is what qualifies the gas to be an ideal gas. Now, I need you to know, having identified those entities, which is the gas pressure for P, volume of gas for V, and thermodynamic temperature for T, for the gas respectively, there is one thing we need to consider, having known the fact that ideal gas obeys gas law. So we need to look into what gas laws is really all about, or are really all about. What are gas laws all about, and how does that have to do, or what does it have to do with ideal gas? Now we have three types of gas laws. There are just three. The first one, we have the Boyle's law. The second one, we have the Chasles law. And the third one, we have the pressure law, also known as Gay-Lussac's law. These three laws are what makes up the gas laws. Now we are going to pick each of this law one by one, and we are going to look at it. How does it relate with a gas? How does it relate with a gas? Those entities I mentioned the other time, the pressure, the volume, the temperature, how does it relate those variables together? So let's start with Boyle's law. Where Boyle's law, was formulated within this date, that is 1627 to 1691. And Robert Boyle was able to come up with a fantastic law, having come out with a beautiful experiment that confirms what he said. And the law states that for a given fixed mass of gas of constant temperature, the volume V of the gas is inversely proportional to its pressure P. What that means is that when I have a constant mass, a mass that is fixed, that is, I'm not changing the mass of the gas, and I'm maintaining the temperature of the mass of that gas or of that gas, the volume of the gas will be inversely proportional to the pressure of that same gas. So based on this principle, we can mathematically conclude that V, which is the volume, is inversely proportional, that is 1 over P, inversely proportional to the pressure. I can as well say that PV equals K, that is when I remove the proportionality sign. If I should remove the proportionality sign, then I will have a constant coming in. And if I made the constant the subject of the formula, the constant will equal to PV. Now, this is just for a fixed mass of gas. And this is just when it maintains, when we are considering a particular volume and pressure. The volume is inversely proportional to that pressure. Now, if we are considering a fixed mass of gas with same constant temperature, but now different pressures and volume, then what is going to be? What's going to be the result of the day? So if I have different pressure P1 and P2 and different pressure volume V1 and V2, as far as the mass of the gas is fixed and its temperature remains constant, then this relationship will change. The relationship I have here will change. So what I will be having in this case is going to be P1 V1 equal to the constant, which is K. Then I will also be having P2, which is the second pressure, then the second volume V2 equal to the constant K. Now the first one and the second one have K in common, so all I just need to do is to combine these two expressions. If I should do that, then I will end up getting this. I will end up getting P1 V1 equals P2 V2, because I'll be substituting this in here for K, and that will give me this. So this explains when we have different pressure as well as different volume of a fixed mass of gas at constant temperature. P1 in this case represents the initial pressure, while the V1 represents the initial volume rather, while V2 represents the final volume, and P1 represents the initial pressure, while the P2 represents the final pressure of that same gas. Now let's see the graphical representation of Boyle's laws, of the Boyle's law. The graphical representation of Boyle's law. We want to see how we can use graph to explain the relationship between the pressure and the volume of the gas. Let's consider this graph. Here on the vertical axis, I have the pressure in Pascal and I have the volume in meter cube. Since the pressure is inversely proportional to the volume, obviously I'll be having a declining graph. I'll be having a declining graph, and that declining graph is going to be a decreasing graph, which is a curved graph in this manner. And that's why you are seeing the graph decreasing. Why? Because as the pressure increases, the volume decreases, because they are inversely proportional. I can as well plot this graph in another way. All I just need to do is to maintain the vertical axis to be my pressure and make the horizontal axis to be the inverse of the volume. If I do that, then I will end up getting this. Here I have the pressure at the vertical axis and I have inverse or reciprocal of the volume. If I do this, then I'll be having a straight line and increasing graph. Why? Because I have inverted the volume. Inverting the volume makes the volume to be proportional in a way to the pressure. But in this case, I'm saying it is the inverse of the volume that is proportional to the pressure, not V itself. It's 1 over V that becomes proportional to the pressure, because it has the it is the reciprocal that we are considering in this case. So I will be having an increasing graph in this kind of. Meanwhile, this still explains what I have here, because if we are removing the inverse, now we'll be having a decreasing graph. So in other words, mathematically, what this has simply indicate is that this is what it has indicated. It has indicated that P is directly proportional to 1 over V. But if I'm considering this, then I will say P is inversely proportional to V, not inversely proportional to 1 over V. That's what I was trying to explain. So they are same thing, but I'm saying it in 2 different ways. Now let's quickly look at the next type of law, gas law. We have the Charles law, which was between 1746 to 1823. What does the Charles law says? Actually, the Charles law was able to relate the volume of the gas to the temperature of the gas, unlike that of Boyle's law. Boyle's law only relate the pressure to the volume. So the Charles law states that for a given fixed mass of gas, still take note of that word, is coming up again. Fixed, the word fixed is coming up right there, which is very, very important. Fixed mass of gas at constant pressure. This time around is not a constant temperature, but a constant pressure. The volume of the gas, which is V, is directly proportional, not inversely. Now this is directly proportional to the temperature of the gas, which is capital T. So the Charles law basically relates the volume to the temperature when the pressure is constant. As far as the mass of the gas is fixed, is constant. So based on this definition, we can then conclude that mathematically V, which is the volume, is proportional to T. If I remove this proportionality sign, it becomes K. So I'm going to be having V equals to KT. If I make the constant K the subject of formula, then I will be getting what I have right here. So it will be V all over T equal to K, which is the constant. Now, if we are considering this same gas occupying different volumes at different temperature, then this expression is going to change. If I'm considering different volumes as at different temperature, as far as the pressure still remains constant and the mass of the gas is still fixed, then the expression is going to be this: V1, which is the initial volume, all over T1, which is the initial temperature, equal to K, which is the constant. Then for the second volume, V2, which is the final temperature, all over T2, which is the final temperature. V2 here is the final volume, rather. V2 is the final volume and T2 is the final temperature, equal to K, which is the constant. Now K is common, so all I just need to do is to substitute for K in this place by putting in V2 over T2. If I do that, then I will end up getting V1 over T1 equals V2 over T2. Now at this point, we'll be able to relate the gas at different volume and at different temperature. Let's quickly look at the graphical representation of Charles' law. How can we use graph to explain Charles' law, just as I did for that of Boyle's law? Okay, so if we are going to look at the graph here, of course we are going to be considering the definition of Charles' law. Now, from the definition of Charles' law, since the volume is directly proportional to the temperature, then obviously we'll be having a straight line graph. So a straight line graph will be obtained since they are directly proportional. So in other words, I'll be having an increasing graph, which is going to look like this. It's going to look like this. Here I have the volume on the vertical axis, and I have the temperature on the horizontal axis. Now, if you consider what I have here, the temperature I have right here is measured in degrees Celsius, meaning that I'm having a rating of 0 to 100 on the positive side of the x-axis, okay, and have 0 minus whatever backward. Mind you, I told you that as far as gas law is concerned, the capital T represents thermodynamic temperature, and thermodynamic temperature is different from Celsius temperature. Thermodynamic temperature is measured in kelvins, but Celsius Kelvin is measured in degrees Celsius. So I only have the range of for thermodynamic temperature, I can have 0 Kelvin, but if I'm considering Celsius temperature, I can have minus 273 degrees Celsius. That is when I convert my 0 Kelvin to Celsius. So that is why this graph is looking like this. Instead of the graph to start from from the 0 here, is starting from here, because the lowest degrees Celsius temperature the lowest temperature is the absolute 0 when it comes to thermodynamic temperature. That is absolute 0, and the absolute 0 is equivalent to minus 273 in terms of degrees Celsius. So I'll be having that. I'll having my graph starting from the absolute 0, where I have minus 273 degrees Celsius. So that's why I have it in this manner. And I told you that it's going to be a straight line, an increasing straight line graph, since V is directly proportional to the temperature. It's just that in this case the temperature is in degrees Celsius. Meanwhile, if we look at the graph in terms of thermodynamic temperature, like what I'm saying is when the horizontal axis is in Kelvin, the temperature is in Kelvin, then what I'll be having will be completely different from this, though it will still exhibit the same explanation I've made here. So in that case, I'll be having the this place to be in Kelvin, the temperature. Why, where I have a 0, I'll be having absolute 0, which is the lowest temperature in Kelvin. So obviously I won't be having any other temperature here because I've rated the graph in terms of Kelvin. Now what I'm simply saying is this is what I have right here. Look at the graph very well. I have the volume here. Now I have the temperature in Kelvin. And here the lowest temperature I have ever is 0 Kelvin. And that is 0 Kelvin is one equivalent to minus 273 degrees Celsius here. So in this case, my graph is going to start from 0, which is the lowest in terms of Kelvin. Okay, up like that, a straight line. So this exhibits the ideal behavior of a gas. Now, if we are to look at this fact that we have here, the fact that the graph is not starting from 0 degrees Celsius explain a phenomenon. If you look at the graph very well, you will observe that at 0 degrees Celsius, which is here, the gas still have a volume. Yes, it still have a volume. Unlike this, at Kelvin, the gas have no volume. But in terms of degrees Celsius, the gas still has a volume in this region. Why? The reason is because the gas liquefies. It liquefies at that temperature. What do I mean? That is, at this is 0 degrees Celsius, the gas liquefied at this is 0 degrees Celsius. Okay, that is why it have an amount of volume right there. And this temperature where the gas liquefied is regarded as the liquefaction temperature. So this is 0 degrees Celsius is more or less regarded as the liquefaction temperature. Now, below the liquefaction temperature, below it, what I mean is that when we go below, if I'm going below, that means I'm moving in the negative direction. Above is in the positive direction. So when I go below this liquefaction temperature, that means I'm going in this direction to the negative. The minimum temperature I'll be having there, which is the minus 273 degrees Celsius, is what we know, or is also known as absolute zero. I've explained this the other time, and from this region I can determine that from the graph. So I can figure out, I can determine the absolute zero right at this region. So this really explains why some gases at 0 degrees Celsius still have an amount of volume. Why? Because at that moment they are liquefied. Those gases are liquefied at that very temperature. So this explains how also absolute zero is being derived. Now at this point we are going to consider the next law, which is the pressure law, and it is also regarded as Gay-Lussac's law, and that falls within the range of the year 1778 to 1850. That was the year this law, within this range, it falls within this range of year. Probably this was a the lifetime. Let me put it as that, the lifetime. Even though Cambridge will not be asking you, to write out the year, the range of year, okay, of the scientist, okay. So, but it's good. Knowledge is not a waste at this very point in time. Now, when we talk of the pressure law states that for a given fixed mass of gas at constant volume, now look at it, something is still reoccurring right here. One is a fixed mass of gas. Fixed mass of gas. Definitely, in all the laws we've considered so far, mass of gas must always be constant. That is the implication. Okay. Now, for Gay-Lussac's law, instead of the temperature or the pressure to be constant, what is constant here is the volume. So the volume is made constant. And when that happens, the pressure of the gas P is directly proportional. It is directly proportional to the thermodynamic temperature of that same gas. So in other words, no wonder why it is called pressure law. Why? Because it relates the pressure of the gas to the temperature. So this law has nothing to do with volume. It has nothing to do with any other factor. Okay, so it only deal with the relationship of the pressure of the gas and the thermodynamic temperature of the gas when the mass of the gas is constant. Now, based on this definition, we can conclude that mathematically P is directly proportional to T, where P is the pressure, T is the thermodynamic temperature. And if I remove the proportionality sign, I'm going to be having P equals KT, where K is a constant. Now, if I make K the subject of the formula, then I'll be having P over T equals K. And this goes for when we are considering a certain amount of pressure in relation to a certain amount of temperature. Now let's talk of when we have the same mass of gas with constant volume at different pressures and temperatures. Okay, if I have this different pressures and different temperatures, what is going to be the relationship between the pressures and the temperature? So this is what we will be having if we are considering different volume, different pressure, as well as different temperature of the same mass, the same mass of gas. So I will be having P1 all over T1 to equal to K, as well as P2 all over T2 to equal, that will give me K. So if I substitute for K for the constant, then I will be having P1 over T1 equals T2 over T2, which is what I have right here. So I have it right here. Okay, T1 all over P1 all over T1 equals P2 all over T2. Now at this point, we shall be looking at the graphical approach to pressure law, or Gay-Lussac's law. Now in this case, I'll be having the pressure at the vertical axis and the temperature at the horizontal axis. Now the graph of pressure law is more or less same as that of Charles' law, so they have similarity. Okay, so pressure law is more or less the same to that of Charles' law. Okay, so in this case, if I'm considering the temperature in terms of degrees Celsius, knowing full well that it ought to be a thermodynamic temperature, which is in Kelvin, but if I'm considering in terms of degrees Celsius, then my origin will not be 0 Kelvin. It's going to be 0 degrees Celsius, meaning that I still have other temperatures below 0 degrees Celsius. So at this 0 degrees Celsius, I still have an amount of pressure on that same mass. Now this justifies what I explained under Charles' law, that at this same temperature, the gas is having a certain amount of volume, and I said it's because they liquefied. Now for a gas to liquefy at a given temperature, some amount of pressure must have been exerted on that gas, and that amount of pressure is simply the pressure in this region at this point when the temperature is 0 degrees Celsius. Now if we go below 0 degrees Celsius in this direction, then I will be having the lowest temperature, which is also regarded as the absolute temperature in terms of Kelvin. Okay, so that's why I said this graph is also the same, it's also similar to the Charles' law's graph. Now at a very low pressure, if the pressure is so low, at a very low pressure, what I will be having, which I've earlier explained, is that I will be having the lowest temperature as well. So in other words, that means as the pressure decreases, you can see the trace, the pressure is declining as we are moving backward. So as the pressure decreases, the temperature as well decreases until it gets to the absolute zero, which is same thing as minus 273. Actually it's minus 273.15 degrees Celsius, but the scientist takes it approximately to be minus 273. So please take note of that. Absolute zero should be minus 273.15 degrees Celsius. That's a raw value, but approximately we are taking it as minus 273 at a very low temperature. So this is what I will be having. Now at this point, we want to quickly consider equation of state. When I was defining the word ideal gas, I said the gas must obey the gas laws or equation of state, and I mentioned the equation of state to be PV equals nRT, and I make sure that you know what each variable in that equation represents. Now I want to look into detail what equation of state is more of or is all about. Now the equation of state is actually obtained by combining the three gas laws. When we combine the three gas laws, I mean the Boyle's law, the Charles law, and the Gay-Lussac law, when we combine these three laws together, what we are going to get at the end of the day is the equation of state, which is what I have here. This is for Boyle's law, this is for Charles law, which we've derived before now, and this is for pressure law, which is a Gay-Lussac law as well. So if we combine these three, we are going to have this: PV over T equals K. That is just very simple. All I just need to do is to combine it, considering the K, knowing full well that they are having K in common. So since they are having K in common, so that will be PV, where I have V here. If you have common one, just make it a single one. So that's going to be PV. V is still here, which is still proportional, so we are still saying the same thing. Then all over T. So I'm still having P here, I'm having V here, we say it as PV. So then all over T, I'm having T here as well, so all over T. So and all that will equal to K. So the implication is that P is directly proportional. I mean, P is directly proportional to T, as well as V is directly proportional to T, while P is inversely proportional to V. That is the implication of the, which explains the all three laws. Now another vital thing you need to know, now the K we have right here, the K we have right here is written as NR. Okay, so K can also be written, which is a constant here, can also be written as NR, where N still remains the number of mole and R remains, R is the molar constant. Okay, R here is a molar constant and N is a number of moles. So what I just need to do is to substitute this in this. So if I substitute for K, I will end up getting PV equals nRT. Don't forget T is actually here. So if I'm substituting, at first it will give me PV over T equals nR. So if you do the rearrangement, you will have PV, then this will go to the other side, then it becomes nRT. I've said it that R is the molar gas constant or universal gas constant. Okay, so you can either call it any of these two. It's regarded as molar gas constant or universal gas constant. That is your R. Now let's see another thing from here. If we are looking or we are considering 1 mole of gas when N equals 1, because I said 1 mole of gas, then the equation I just gave you guys will change. The equation I just gave you will change. So the equation now will now be PV equals RT. Remember there was N initially. The N now is 1. So it becomes PV equals RT. Or you can say PV over T. But in this case I'm making it VM. Because I intentionally do this because we are considering just 1 mole. So VM in this case is standing for the molar volume. Okay, the VM here is standing for molar volume, and molar volume simply means volume occupied by 1 mole of gas, and that's what we are dealing with. We are considering 1 mole of gas. Okay, so that's why I make it Vm. Now the value of our R, which is the molar gas constant or the universal gas constant, is 8.31 per mole per Kelvin. You need to take note of that value. It's very important. That is the value of the molar constant. It doesn't change. That is just the constant, is the constant value. Okay, so that is just for R. Okay, now at this point, if I am to look at the formula I gave for the equation of state, which is PV equals nRT, there are certain factors that must be fulfilled for that formula to hold. For the formula to become valid, okay, this following factor must be fulfilled. So in other words, PV equals nRT is only valid for a fixed mass or amount of gas. Is only valid for a fixed mass or amount of gas, meaning that the gas must have a fixed mass or a fixed amount. Okay, or just like a fixed number of mole. That's what I mean. Then second condition is that the gas must be an ideal gas, meaning that it must obey gas laws, or the fact that it have a constant mass, of course, makes it a gas law. So these are the two major conditions that must be fulfilled for this equation to be valid. Now there are other things we've got to know, and this has to do with what we call Boltzmann constant. Boltzmann constant. We will need Boltzmann constant in the course of this lesson, because at a point we are going to come to relate Boltzmann constant to some other parameters, some other things, to able to figure out how molecules or particles in a gas behave, and we are going to relate it with the pressure, the volume, and the temperature, as well as energy of that exerted or obtained or exhibited by the gas. So the question is, what is Boltzmann constant? Boltzmann constant is a physical constant relating average kinetic energy and absolute temperature. It relates the average kinetic energy and absolute temperature, which is also known as thermodynamic temperature, contained in each molecule of an ideal gas, and it's obtained by taking the ratio of two constants, namely gas constant and Avogadro's number or constant. Okay, so these two constants, the ratio of these two constants gives us the Boltzmann constant. But meanwhile, it is used for relating the average kinetic energy and absolute temperature. We are going to see how this plays out in the course of the lesson. How do we finally, or can we use Boltzmann constant to derive the relationship between average kinetic energy and absolute temperature? Of course, we are going to do that in the course of this lesson. Now, knowing full well I said the ratio of these two constants gives us the Boltzmann constant, then mathematically I can conclude that Boltzmann constant Kb equals R over Na, where my R is the gas constant, which is also known as molar gas constant, and my Na is the Avogadro's constant. So here is the mathematical expression for Boltzmann constant. Now, Boltzmann constant have a constant value as well, and the constant value of Boltzmann constant is 1.38 times 10 raised to power minus 23 joule per Kelvin. This is a constant value, okay, and you need to know it. At times, of course, it is usually being provided in the second page, or rather the back of the first page of your question paper, either for paper 1 or for paper 2. Okay, so you don't really need to cram as such, but it's cool if you can memorize. That is going to be an interesting one. Okay, but take note of this value. It's very, very important because you will need it during the course of solving questions together. At this point, let's consider Brownian motion. Brownian motion. Actually, this aspect of the topic is one of the interesting aspects I so much cherish because of the beautiful work one of the scientists carried out, to justify the evidence of the presence of particles in matter, of which gas is one of the state or the types or the form of matter. Now, the Brownian motion was first carried out, the experiment was first carried out by a Scottish botanist who happens to be from Scotland, and the name of the botanist was Robert Brown, and he did that in 1827. Now, what this guy did was so fantastic. What he did was, to carry out some experiment in the laboratory, and based on the experience of the experiment, he was able to discover that certain particles, or particles in general, matters, they move in a particular pattern, particular way, and he discovered that was due to the generation of pressure from the collision of the molecules of such matters. Okay, so this was also used to explain the behavior of the molecules of a gas. Okay, so on this ground was Brownian motion defined. So the question now is, what is Brownian motion? Brownian motion is the rapid random molecular motion, movement of gas in a container due to the generation of pressure from the collision of the gas molecules. There are key things there: the motion of the gas, what causes the motion, in the container. And the motion is simply a random motion, random molecular motion, and not just moving, but it moves rapidly. It's a rapid random motion. Then what causes it was actually the production of pressure due to the collision of the gas. So the collision of the gas creating pressure or mounting pressure on the container, okay, determines the rapidness of the motion of the gas molecule and the way the gas molecule moves in the container. And this was actually done, it did that by using a pollen grain or particles. What it did was to subtend the pollen grain in a fluid, or fluid could be a liquid or gas, okay. And after doing that, he examined that under a microscope, and what he observed was wild. From what he observed, he was able to make some inferences, was able to make some conclusion. And some of the conclusion he made was the fact that since the pollen grain constantly moved randomly, because he discovered that the pollen grain was actually moving randomly, that confirms that the particles of gas, which could also be solid or whatever, okay, as far as it's a matter, okay, so the particle of gas are constantly moving. So that's number one observation he made from the experiment. He discovered that the particle of matters, of which gas is one of it, are constantly moving. The second observation he made was the fact that matter is made up of tiny particles, meaning that the size of a particle of a matter, which could be a gas, is very, very tiny, very, very small. Okay, now how does the whole thing play out during the experiment? Let me show you. Take a look at this video, which tells us how the particle plays out. You will see from the video that some molecules were moving randomly, colliding with themselves. All these molecules in red, colliding with themselves. And as they are colliding with themselves, they were indirectly as well colliding with this blue object, which also represents another molecule. Okay, the same thing happened when he used the pollen grain. Subtending the pollen grain into the fluid, the molecules of the fluid were colliding, and as they were colliding, they were as well colliding with the molecules or the particle of the pollen grain, and that makes the pollen grain to be moving randomly in that same container. This was exactly what can be likened that was observed when Robert Brown was conducting the experiment. And so with this, you will notice that the motion remain constant. They keeps on moving, they keeps on moving randomly. It's just constant, not stopping. And the particles are just so tiny, we can't even see the particle with our physical eyes, but with the aid of a microscope. This was what Brownian motion was really all about, and this alone justify the evidence of particles in a matter, of which gas is one of it. So that means all gases contains particles or molecules. Now at this point, we want to see how molecular movement of the gases causes the pressure exerted by the gas. So the question is, how does molecular movement causes the pressure exerted by the gas? You will notice that as I was showing you the Brownian motion of the gas, you see that the molecules were eating themselves as well as eating the container, the wall of the container. So as they were doing that, they are mounting pressure. Okay, and the mounting of pressure on the container, okay, and on themselves stimulates the rapidness of their movement as well as their random motion. Okay, so the thing we want to do now is to see how that really plays out. How does the molecular movement cause the pressure exerted by the gas? This is what we'll be looking at this very moment. Okay, so from here, the first thing is that the molecule eats. It eats and rebounds. It eats and rebounds from the wall of the container. This is the way the molecule of the gas mount pressure. The secondly, the collision between the gas molecule and the wall causes change in momentum, which give rise to force or impulse. So as the molecules of the gas collide with themselves and also to the wall, there is a change in the momentum of the molecules. Their speed or their velocity changes. And since momentum is mass times velocity or mass times speed, then we can as well say the momentum changes, which is obeying the Newton's second law. And this gives rise to force. Since Newton's second law confirms the application of force on an object in respect to its mass and acceleration, and also confirms impulse, then this gives rise to force. Then number 3, the average of many impulses. That is when we are considering all the impulse of the molecules. At least we are considering, okay, the impulse of one molecule to another molecule to another molecule. Then we bring all the impulses together. It gives a constant force and also pressure. So from the impulse, I can get a constant force, knowing full well that impulse is actually Ft, and same impulse is also equal to change in momentum. So since impulse is Ft, then my force will equal to change in momentum over time, which gives a constant force. That means that is our constant force. Then if we are considering the area of the container, then we will be talking of the pressure, which is force over area. Then number 4, these processes, I'm talking of number 1, number 2, and number 3 I've given out. Those processes shows the gas molecules are in random motion. So as far as from the impulses, we can fashion out the force as well as the pressure. So it's really justify the fact that they are in random motion. Again, as far as we can fashion out the fact that they collide with themselves, we can figure that out. Then it shows that the gas molecule also move in random motion, because when there's collision, all the molecules are colliding, they move not in a straight line, they move at different directions, so randomly. Then from here, we want to see how does change in temperature and particle size affect the motion of gas molecules. How? does change in temperature now and particle size affect the motion of gas molecule? If we increase the temperature, what will happen to the motion of the gas molecule? Or if we decrease it, if we increase the size of the particle of the gas, how will it affect the motion of the gas, or what effect will it create on the gas molecule? So this is what we want to see and want to quickly justify. Now I need you to know that with increase in temperature, the particles of the gas expand and move faster as they gain kinetic energy. Okay, once we increase the temperature of the gas, what we are going to notice is that there is going to be an expansion. There's going to be an expansion in the particle of the gas. Yes, in the particle of the gas. Then, because of this expansion, there's going to be a sporadic increase in the movement of the particles or the molecules. Why? The reason is because there is a gain of kinetic energy from the temperature. But there can be increase in temperature without an application of heat. So I need to supply heat. It is the heat that causes the change, that supplies the energy rather, and causes the change in the motion of the particles. And when an object is moving, the only energy such an object can exhibit is the kinetic energy. Apart from that, as the kinetic energy increases, that will result into increased collision. So it results into increased collision rate. So the more the molecules of the gas will collide with themselves. But what if we increase the particle size? What is going to happen? An increase in particle size will result into more frequent collisions to occur. Reason being that normally the molecule of a gas is very, very tiny, very small compared to the spacing between them. The spacing between them is greater than the size of the molecule. Now, when we increase the size of the molecule or of the particle, that means we are going to take more space. Okay, the spacing between them will reduce drastically, and that will enable the particle to collide the more because there is less spacing between them. Meanwhile, you have to be very careful not to confuse this with the weight of the molecule or the particle, because the weight is different from size. Weight does not depend on the size of an object. An object can be robust and be weightless, and there you see another object that is as tiny as anything but weightier. Okay, so weight does not depend on the size of an object. So in this case, the weight cannot be likened to the size of the object. In fact, the weightier or the more massive the particle or the molecule, the slower the speed or the velocity of the molecules, because weight or mass determines the inertia of a body. Okay, so that alone explains the fact that the weight of a body have nothing to do with the size, the weight of the molecules. Okay, at this point, let's quickly look at basic assumptions of the kinetic theory of gases. We want to look at the basic assumptions of the kinetic theory of gases. Some of the assumptions that were made from the theory of gases, the kinetic theory of gases, or which is also known as molecular theory of gases, are: number one, all atoms or molecules or particles behaves as identical, hard, and perfectly elastic spheres. This is one of the major assumptions that was made as far as the kinetic theory of gas is concerned. So if we are considering an ideal gas, okay, and when we say ideal gas, something that naturally will not have happened, naturally will not have occurred, but we are not looking at it ideally. What if it happened? Okay, so we are looking at a theory to back up our assertion as regards that. Okay, so the thing is the fact that ideally all ideal gas or gases, all ideal gases have identical molecules or atoms or particles, and those molecules are hard and perfectly elastic. Number two assumption is that the volume of particles or atoms or molecules is negligible compared with the volume of the container. So it can be neglected. We can easily neglect the volume of particles or atom. Why? The reason being that each particle are so tiny. So they are so tiny. So when we have numerous particles like that, tiny, the volume will still not amount to anything. So the volume of the particles or atom is negligible when we compare the volume of the container they are occupying. The third assumption is that there are no forces of attraction or repulsion between atoms or molecules. There are no forces of attraction or repulsion between atoms or molecules. The reason is because there is no bond between the atoms. The bond that exists between them has been weakened as a result of the application of heat. Remember that gaseous object can only be obtained when its solid form has been broken down to form a liquid, and the liquid has been broken down to form the gas. Okay, so the bond are weakened as a result of the application of heat, and as the bond weakens, the more we have a gap or space between the atoms or molecule. So in other words, the force that exists between them will be more or less negligible, or we can just do without it, since the gap between them is wider compared to that of solid or liquid. Number three, Number 4 rather. Particles or atoms or molecules are in continuous random motion. They move randomly. I've explained this using Brownian motion. So ideally, all gases moves randomly and they move continuously in random motion. Number 5. Time of collision negligible to time between collision. What do I mean? The time it takes to collide is negligible to time between the collision. So there is a great variance between the time of the collision when the collision happens and to time between the collisions. That is the time when both has hit themselves and separated. So that's what I said. So it's very, very negligible. It's more or less equal to each other. So that's what we are actually saying. So when we have two molecules colliding with themselves and another two molecules colliding with themselves, the time of collision is negligible between the both of them. Now at this point, we want to see how we can deduce this relationship. Okay, where P is still our pressure and V is the volume, and N here is the number of molecules, while M is the mass of the substance, and C is speed. Meanwhile, this symbol simply means mean speed, and because we are having raised to power 2, it becomes mean speed square. I'm going to explain this more as we go on in the course of the lesson. So our major objective right now is to see how we can relate the pressure, the volume, and these other variables in this kind, how we can obtain this equation. Okay, so we want to see how we can relate the whole variables using this equation and deducing how this equation was obtained. Okay, so this is what we are going to be doing right now. To do this, let's consider a container, a square container with a molecule inside the square container. Let's take this to be our, which is our result. This is our horizontal axis X, this is the vertical axis Y, and we have another axis Z there, Z. Now we are considering this spaced cube container of length L and a moving mass M of molecule with a speed Cx moving towards the wall in one direction. This is one of the wall of the cube. This is another wall. We have another wall here. We have another wall at the left hand side right here. So we have another wall. So we have different walls that makes up. In fact, a cube have about 1, 2, 3, 4, 6 walls. 5, 6. That's 6 walls. Okay, so let's consider this mass of molecule moving towards this wall with a velocity of Cx. Now, when the molecule moves in this direction and collide with the wall, of course, there's going to be a change in its velocity. And knowing full well that the molecule have its own mass, the product of the mass of the molecule and the velocity to which it's used to collide with the wall and to bounce off from the wall towards its initial direction, okay, will give me its momentum. Okay, meaning that the product of its mass times the velocity it used to collide with the wall will give me its initial momentum. When it bounces off from the wall towards its initial direction, it will give me its final momentum. So meaning that the momentum it used to collide with the wall will be the initial momentum. So in other words, when the molecule collides with the wall, the initial momentum P1 in the x direction, because the molecule is moving in this direction, you can see the direction of the arrow. Okay, so in the x direction will equal to m times cx, where cx there still represents the velocity of the molecule in the direction of x, while the m still represents the mass of the molecule. When the molecule hits the wall and bounces back, then the final momentum of the molecule P2 in the x direction will equal to minus the product of mass times its velocity. Why do we have minus? Because the object is going to move back in its initial direction. How do I mean? What I mean is this: the object is starting off from here, moving like this. On hitting the wall, it bounces back to its initial direction. So that direction of bouncing back is simply opposite to the first direction. That is why it is negative, and it's moving in the left direction, which is negative. Why? When it was initially going, it was moving in the positive direction. Now again, the velocity is the same because the molecule cover the same length of the same length of the cube. Okay, knowing full well that every cube have equal length. Okay, so from here to here is same thing as from here back to where it starts from. And again, it moves with constant random motion. I've said that earlier, that all molecules move with constant random motion. So since their motion is constant, definitely their speed or velocity is also constant. Either it is moving towards the wall or bouncing off from the wall. So it's moves with constant velocity. Now with what I have here, having known the final momentum and the initial momentum, I can from here determine the change in the momentum. Okay, so to determine the change in the momentum, I will simply subtract the initial momentum from the final momentum, and that will give me this. So this is the final momentum. This is the final momentum. Initial momentum rather. Here I have the initial momentum. Here I have the final momentum. It's still the same thing as if I have the final momentum here and the initial momentum here. Because if I have the final momentum here, I'll be having minus mcx minus mcx. This is what I actually mean. This is what I should be having if I'm subtracting the initial momentum from the final momentum. I will be having minus mcx, then minus mcx. Since the final momentum is mcx and the initial momentum is since the final momentum is minus mcx and the initial momentum is mcx, and I've said to find the change, we'll take the initial away from the final. So this will give me minus 2 mcx. Okay, so this will, the negative here is just to tell me that, just to give the direction. Okay, the direction of the change is to the left. It changes to the left. It's just to give me the direction. So the sign does not really matter. But if I'm considering the fact that the object is starting from the right hand side and moving towards the left hand side, hit the wall and bounce back to the right hand side again, then this particular equation is perfectly correct, which will be 2mcx. Of course, it's still the same thing. The only difference is the direction. Alright, so from here, if we consider this, having known that the change in the momentum is 2mcx, then I can easily figure out the other parameters that has to do with the direction of the momentum. Knowing full that the object starts from here, the molecule starts from here and moves in the direction, of course it covers a distance L. Then bouncing back to this direction covers another distance L. So with that, I can easily conclude that the total distance covered after collision with the wall equals twice of L. That is L plus L, which will give me 2L. Okay, so that will give me the total distance covered by the molecule after collision. So with this, I can easily figure out the speed, the time it takes, the time now it takes the molecule to cover the total distance. Okay, the time it takes to move from here to here and from this wall back again to this place. So to determine the time, knowing full well that speed equals distance over time, so if I make time the subject of the formula, it will become distance over speed, making time the subject of the formula. And since the total distance covered by the molecule is twice of L, and the speed of the molecule is Cx, then I can conclude that the time taken for the molecule to cover the total distance, that is to hit the wall and return back, will be T equals 2 into L over Cx. How did I come with this? How did I come up with this? This time here is simply the time taken for the molecule to hit the wall. Okay, to cover distance L, just to hit the wall. But the time it takes to hit the wall and to return back will be twice of the time it takes to hit the wall. And that's why I have 2 times the time it takes to hit the wall here, which is L over Cx. And that's what I have right here. Now from here, having determined the time it takes to cover the total distance, and having known the change in the momentum of the molecule, I can from here determine the rate of change of momentum. I already know the change in momentum. I already know the total time it takes to cover the total distance. So the rate of change of momentum now, which is delta P over T, will equal to 2mxc, that is, just substitute the what we have here, what we got for change in momentum here, come and substitute right here, then you have this, then divided by what I have for the total time taken, which is twice of L over Cx, then you substitute for t, which will be divided by that. If you do your mathematics very well right here, you open up the bracket, you will be having 2L over Cx. And because this division, when it changes to times, Cs go up, then 2L comes down. And in that manner, I will be able to have one of the Cx cancelling one of the C. I will be able to have twice of Cs rather, because in this case it's going to be Cx times Cx. This is what I mean. Let me write it out. From what I have here, it becomes 2 times m times Cx. And see this division, if I change it to multiplication, then it becomes multiply by Cx will go up. So that becomes Cx all over 2L. If I open up the bracket, 2L. So that becomes the denominator right there. So in this case, 2 will cancel out 2. Cx times Cs will give me Cx square, and that will end up giving me mcs square over the length I have here, and that is what I'm having right here. The result is what I have right there. So that means change in the rate of change in momentum equals to mcs square over L. Now from here, let's quickly take a look at the important aspect of this. Having determined the rate of change of momentum from Newton's second law, force F is also equal to the rate of change of momentum, which is delta P over T. And I will determine delta P over T to be this initially. Now I need us to recall that pressure is also force F over area A. I've said this earlier on, where the area A is L square, that is length times length, since a cube have equal length. So the area of one of the side of the cube will be length times length, which will give us L square. Now I'll be able to determine the area, and I already know my force to be equal to the rate of change in momentum, which is the whole of this. So what I will simply do now is to substitute. I will put in this right here, then I will put this right here. Okay, so I'm substituting. If I do that, then I will end up getting this. So the pressure P on wall produced by a single molecule, that is this molecule here, a single molecule, is P equals what I've substituted, which is the whole of divided by L square. If we do our arithmetic very well right here, this over this divided by this will give me P equals mcs square over L cube. That is L times L square, because division will change to times, and so it will now become inverse of L square, which is 1 over L square, and L square will multiply L to give me L cube, and 1 will multiply the whole of this to still give me back that. Now remember, L cube is same thing as volume. Length times length times length, that is volume of a cube. So in other words, I can conclude that L cube equals V, which is the volume of the cube. So anywhere I see L cube, I'll be slotting in V. So if I do that right here, then I'm going to get P equals MCS squared all over V. Now what I've done is that I have replaced this L cube by V, since L cube equals V. Okay, right from here, we move straight away to see what happens if I have more than one molecule in the container. If I have more than one molecule, like what I'm having right here, I'm having 3 molecules. So if I'm having more than one molecule, then what is going to happen to the relationship we've derived right here? To the relationship we derive right here, what will happen to this relationship? Because this relation is only meant for just one molecule in one direction. Now, considering that for 3 molecules, or more than 3 molecules, it's not necessarily it should be 3, it could be more than 3. Okay, so we are considering for number of molecules, which is capital letter N, in the cube, with each of their x component velocity, which is cx1, cx2, then cx3. And that is what I have here. And if it is more than 3, then I can be having cxn, that is for a number of molecule n, which could be more than 3. Okay, so from what I have here, all I just need to do is to simply find what I call the square of each of the velocity. If I find the square of each of the velocity here, that will be cs squared. Then I add them up. That's going to be cs squared, s1 squared, then cx2 squared, then cx3 squared. Okay, so adding them up will give me the resultant velocity. Okay, which is going to equal to cx squared, where cx is the total velocity. Okay, and the square there is to tell me that it's going towards the wall and returning back to its initial position. That's why I'm having square. Okay, so if I come to substitute that in the relationship we've derived, which is P equals MCS squared all over V. Definitely for CS squared, I will be slotting in what I have right here. If I find the square, so I'll be having this for that. And finding the sum, finding the average. And to find the average of that, average is simply dividing the number of the velocity, adding each of the velocity, the square of each of the velocity, and dividing by the number of the velocity, or the number of the molecules rather, the number of the molecules. So if I do that by finding average of the total velocity square will equal to the sum of each of the square of individual velocity or speed then divided by the total number of molecules. Okay, now I need us to know this, that this symbol right here, this very symbol right here, is known as mean square velocity. Is regarded as mean square velocity or speed, and this should not be mistaken to the average molecular speed. This is not the same as average molecular speed. This is just mean square velocity, not average molecular velocity or speed. Okay, having known this, we can then from here determine what the relationship is going to be between the pressure, mass, the velocity of the speed, and the volume. Okay, so all I just need to do is, wherever I see this, I will be substituting the mean square velocity times the number of the molecule. Because if I make this the subject of the formula, if I make this the subject of the formula right from here, then I will end up getting this times this. So if I now come to substitute in this expression right here, this particular expression, then I will be having this substituted for this, for the product of this and this, which is n. So if I do that, I will end up getting P equals m times n, then times the mean square velocity, then divided by volume. Okay, what I've simply done is that I have replaced the whole velocity here in bracket by this, and this, since this expression relates them together, so I've replaced that with n mean square velocity. Now if we are considering a molecule moving in 3D, what do I mean? Moving in 3 dimensions with resultant velocity c square. It's going to have component velocity in 3 dimensions as well. What I mean is this. Let's assume that this molecule right here is the only molecule in this container, while these other 2 are not there. Now, if we are considering the movement of this molecule in x direction, and then in y direction, and then in z direction, this is what I mean. If I'm considering x direction is already indicated, then y direction, that is going to be upward. Don't mind, but just to indicate, this is y direction. Then in the z direction, that is in the direction, this is x direction. Okay, then that means this molecule is moving in 3 dimensions, and the velocity, the resultant velocity of the molecule in the 3 dimension is c square, and that resultant velocity is actually gotten from its component velocity in the 3 directions, because this will have its velocity, which is cx, then this one will have its own component velocity, which is cy, then this also have its component velocity, which is cz. Okay, so With that, we can conclude that c square equals cx square plus cx square plus cz square, or cz square. Since I said c square is the resultant velocity, so meaning that is an add up, a summation of the square of individual velocity in each direction, x, y, z. Now, this is just for a molecule in 3 dimensions. Now, if I'm considering for all molecules, all the molecules in the sense that for x, like I'm considering for I'm having more than one molecule now. Now, the 3 molecules moving in x, moves in y, moves in z. Definitely, I will need to find the average or the mean square velocity of each component. So in that case, for all molecules, we find the average as the mean square velocity, which equals to the mean square velocity in the x component, and this is actually the resultant in the s component, okay, then plus the mean square velocity in the y component, then the mean square velocity in the z component. So with this, I'll be able to get the resultant mean square velocity or mean square speed. Okay, from what I have right here, knowing full well that molecules move in random direction, I mean, they move with random motion, they move randomly. And I've said it earlier that moving randomly does not mean they move at variant. They move with a constant random motion, meaning that their velocity remains consistent, is constant. So that means each component of the velocity, each velocity component right there will be equivalent to each other. What do I mean? That means the component of the velocity in the x-axis will equal to the component of the velocity in the y-axis, and will equal to the component of the velocity in the z-axis. Okay? And don't forget that we are dealing with the mean square velocity in this case. And since they are all equal to each other, from the equation I had the other time, from the resultant mean square velocity, that means anywhere I see cy square, the mean square velocity for the y, for the z, I can slot in the mean square velocity for z, since they are all equal to each other. So if I do that, I will end up getting the mean square velocity, the resultant mean square velocity to equal to thrice the mean square velocity in the s component. What I've simply done is that I have replaced each of these in the equation I got the other time with c square, cx square, which is the mean square velocity in the s component, and adding them up together will give me 3 into the mean square velocity. Now what I want to do is that I want to relate this. Actually, what I have here is making this the subject of the formula. If I make this the subject of the formula, I mean this, the subject of the formula, then it will become this divided by 3, which is what I have right here. Now, if we can recall, for number of molecule n moving in same direction, for number of molecule m moving in same direction, there was a formula we derived back then, and this was the formula, which is P equals m times number of molecule, then the mean square velocity in the s component over volume. Now, if I'm considering that, knowing full well that the mean square velocity in the s component is already this, which is what I have right here, then all I need to do right here is to substitute for this in this by putting in the whole of this. Now, anywhere I see this, I'll be placing this right there in this place. And when I do that, I will end up getting this. This is what I will end up getting. If you do your substitution correctly, you will get this expression. Now, this expression we derive here, which is PV equals 1 over 3 nm resultant mean square velocity, is for number of molecules moving in same direction but in 3 dimension, which is 3D. So this formula is only applicable for number of molecules moving in same direction and also in 3 dimension. So that is when this is applicable right here. This is applicable. But if it is number of molecules just in one direction, then we'll be talking of this other formula, which we have derived earlier before now. If we can recall, density is actually mass over volume. And if we are considering one molecule, that is a molecule, density rho will equal to m over v. But for number of molecule or more than one molecules or gas, for more than one molecule or gas, then I will be having rho, which is density, equals number of molecule times mass, then all over volume. All I just did is to multiply the density for each molecule by the number of molecules I have. Now, the product of the number of the molecule times the mass, m, is equivalent to the total mass of the molecule. What do I mean? What I mean is this: n times small m, which is mass of the substance, times the number of molecule, is equal to capital M, which is represent the total mass of molecules, which is very straightforward. So with this, with what I have here, if I go on and make this the subject of the formula, I'm making nm the subject of the formula, I will be having rho v. So nm will give me rho v. Then I will come back to this form expression right here, the expression we derived here, and substitute for nm. If I substitute for nm here, definitely this will change to rho v, and that will end up giving me PV equals 1 over 3 rho v, then mean square velocity. But meanwhile, since v is common on both sides, v will cancel v, and that will end up giving me this. So that will be p equals rho, then the mean square velocity all divided by 3. The v has cancelled out since that there's going to be v on the both sides. Now we need to note something right here. Take note of this. When we square root the mean square velocity, if we find the square root of the mean square velocity, it's going to give us what we call root mean square, which is RMS rather. The CRMS in this case is still regarded as the root mean square velocity. This can only be obtained when we find the square root of the mean square speed of this. The mean square speed is what will give us this when we find the square root. Now from here, let's quickly look at how we can deduce the average translational kinetic energy of a molecule in respect to the time t. In respect to the temperature rather, not the time. In respect to the temperature, capital T. We use small t to represent our time. So I'm using capital T to represent the temperature. Okay, so we want to see how we can deduce the relationship between the kinetic energy, average kinetic energy, and the thermodynamic temperature T. Let's take a look at that. If you could remember our Boltzmann constant, our Boltzmann constant Kb is actually R divided by Na. So what I did now was to make R the subject of the formula, which end up giving me Na times Kb. Also, for the equation of state that we derived, PV equals N RT, where each variables here represents what they stand for, which is pressure, volume, number of molar, gas constant, then temperature. Now, if we use these two equations right here by substituting for R in this, using this Boltzmann constant relationship, that means anywhere I see R, I'll be putting in this or substituting for this. Then what I will be having in this case is that this will become PV. By combining, this will become PV equals small n, then capital Na Kb T. What I've done is that I have replaced my R with Na Kb, which end up giving me this right there. So PV will now equal to that. Now I need us to recall when we were discussing about Avogadro's constant. I said Avogadro's constant is equal to the number of molecule over number of mole, meaning that Na equals N over small n, where the N there is capital N over small n. So if I make the capital N, which is number of molecule, the subject of formula, then I will end up getting this right here. Now if I go ahead and substitute, if I go ahead right from what I have and substitute in this expression I have up here, NA, by bringing in capital N, then I will end up getting another relationship, which is this. So in this case, PV becomes N, which is number of mole, times Boltzmann constant Kb, then times thermodynamic temperature T. What I've simply done is to replace NA with N, which gives me this. Now, by combining the above expression right here, this one, with the other expression for number of moles moving in same direction but in 3 dimensions, which we derived earlier on, which is PV equals NM. See, I mean this is what I mean. Let me write it out for better view. I mean PV equals N M, then mean square speed then all divided by 3. This is the formula we derived the other time for number of molecules moving in same direction with 3 dimensions or in 3 dimensions. So if I combine this formula right here with this other formula we derived using Boltzmann constant and equation of state, knowing full well that PV is common to both equations, then I will definitely get an equation like this. An equation like this, because this is combined with this, and so PV will substitute PV, so NKB will come in, or you can simply put this in this. So that will be the whole of this will be coming here equal to the whole of this. It's still the same thing, just interchanging, and the formula is going to be the whole of this I have right here. The whole of this I have right here, if you do the right substitution. Now from here, N rather, the capital letter N, which is number of molecule, will cancel out each other's, because there's N on both sides. So N here cancel this other N. And if that happens, I'll be left with 1/3m, then the mean square speed equals kbt. Now 1/3 here can be written as 2/3 times 1/2, 2/3 times 1/2. Why? Because 2 will cancel out 2 and it will still end up giving me 1/3 back. So I have not missed anything. So meaning I can write this expression as this. Now with what I have here, if I bring this to this other side, if I migrate this value to this other side, then I will be having 3/2. Okay, so in other sense, I'll be having this. So this one will now become 1/2m, that is, I'm having the whole of this, leaving this one out, equal to 3/2, because when 3 comes to this side, it's going to be at the numerator and 2 will be at the denominator. If you bring it back again, it will end up giving you this also. So it will now be 3/2 Boltzmann constant times temperature. Now I need us to know something right here. That this particular expression here is what we call the average translational kinetic energy. So it's regarded as average translational kinetic energy of the molecule. So if that is the case, definitely that means I can rewrite this expression as kinetic energy, average kinetic energy, which is Ke equals 3 over 2 Boltzmann constant times the temperature. So with this, we have successfully been able to determine the relationship between the average translational kinetic energy, which is this, and temperature, which is this. So in other words, from what I have right here, it can be deduced that average kinetic energy is directly proportional to the temperature, meaning that temperature is a measure of the average kinetic energy of gas molecule. It's just as simple as that. So with the knowledge you have before, temperature is a degree of coldness or hotness of a body, that is not just enough. So temperature with this expression can as well be defined as a measure of average kinetic energy, since they are directly proportional based on this expression. With this, we've been able to see how kinetic energy, average kinetic energy, can be related to temperature, and now we can use Boltzmann constant to relate the average kinetic energy and the thermodynamic temperature, which justify the definition I gave for Boltzmann constant. Now at this point, let's quickly consider some questions. We'll be able to see everything we need to know as far as ideal gases is concerned. Are concerned. So at this point, I want to look at questions based on what we have learned so far. And right here, we'll be looking at the first question, which you can try to do on your own. Just pause the video and check up the questions. The first question here is this. The continuation of this first question is this. The question continues right here. So this is also the continuation of the first question. Then next I have the second question right here. The continuation of the second question is this, as well as this. This is still the part of the second question. Then the next one, I have the third question, which is this. And the third question is this. And the continuation of the third question is still this. Then we have this under the third question, which is the end of the whole question. With this, you can just pause the video, lay your hands on it, based on what I've taught you, walk through the questions, and you can try to forward your solution to the email given below. Any clarification you want, you can as well forward it to the email below. If you need any assistance as per the solution to this question, you need correction, you can as well forward a mail to the email written below. On this note, we shall call it a day from here, and I'll be looking up, expecting to see you again in the next video. Do have a great time. Thanks for watching. It's nice to meet you. Expecting one more time in the next video, and keep enjoying the best of every video in this channel. Bye for now.